Okay, so we're going to start with 10.1 correlation. So they measure, remember now, this is bivariate, two variables, x and y, so we form scatter plots.
Right.
So each individual has two measurements, and we want to see if they're correlated. So here the two measurements are body temperature in degrees Celsius and head circumference. And for this sample of paired data, what does R represent and what does rho represents? Well, R is the statistic and rho is the parameter.
Okay.
R is the statistic for the sample, rho is the parameter that R is estimating for the population. So let's see which one reads the best. R is the statistic represents the value of the linear correlation coefficient computed from the sample data, and rho is a parameter represents the value of the linear correlation coefficient that would be computed by using all of the pairs. So A is the best read already. It can't make it any better than that. That's what it means. See, if you could measure all of them. And then, so for this one, what do you suppose R would be for these two variables? Do you think body temperature is related to head circumference?
R would be the Celsius or the degrees.
No, here's what we're saying. We're on the scale from plus one to minus one, and zero's in the middle. They're asking you, what do you suppose R would be? Is there a relationship? Estimate the value of R. Remember, we put
8.6.
No. It's not a measure. It's not a measure of one of the variables. It's a measure of their correlation. Remember, this is minus CVR and this is plus CVR. If we end up in the middle, it's essentially zero. That there is no correlation.
Okay.
So I would estimate it being zero. There's really nothing that temperature and head circumference can't be related. Not if you have a large enough sample.
Yeah.
So that's what they're looking for.
Okay.
See, it's likely there's no correlation between. It's likely that they are strongly negative, strongly positive. See, they're asking you which one of these regions, of three regions, would they be in? Would they in the right tail, the left tail, or in the middle? In the middle, so that's because there's probably no correlation. So we'd estimate it to be zero. Okay, that's the idea. And then they have this, what if you measured body temperature in Fahrenheit instead of Celsius? You think that would change anything? Not really. R does not change because R is not affected by any converting the values to different scales. Read it wrong. Oh, it says, I want the one that says not changes. There we go. I didn't see the not. I was missing the not. By the way, A is true too, but it doesn't have anything to do with this. You can flip the X and the Y and you'll still get the same correlation. It doesn't matter. But you're just calling one X, the other one Y. Yeah. You just flip them and it'd be the same thing. Okay.
Does that go for correlated ones as well?
Sure.
Okay.
No matter what, the correlation coefficient will be the same.
Okay.
What we determine what that correlation coefficient means doesn't change.
Okay. Is that another way to Y with it? Is to change the X and Y?
Not really.
Okay.
Not really. 20 different statistics students are randomly selected, and once again, same thing, body temperature and head circumference. It's found that R equals 0. Does this indicate there's no association?
Correct.
Yes?
Yes, there is no association.
It means there's no linear.
Okay.
But that doesn't mean it can't be a nonlinear.
Was that?
Yeah. See, it could be a parabola.
Okay.
Or it could be a couple of outliers. So it's just that, if you read the answer, no, because while there's no linear correlation, there may be a relationship that's not linear.
Okay.
Yeah, because if you had a parabola that fitted the data, it wouldn't necessarily fit a straight line, so the R would be 0, or effectively zero, but you wouldn't know it, that there was a relationship, unless you looked at the scatter plot. And then this one we have, you got this one wrong last time. Let's see if you can get it right this time. If we find that the linear correlation between concentration of carbon dioxide in our atmosphere and the global temperature that indicate the changes in the concentration of carbon dioxide cause changes in the global temperature. No, they're just correlated. They don't cause anything. It could be caused by something else. They could cause each other, but the correlation coefficient doesn't promote that. Okay, so here's what they're going to do. They're giving us 5 numbers for correlation coefficients. I point out that here's one that's exactly -1. That means the points will be on a line.
Okay.
That's negative slope. This one's almost the same. It's almost -1. And then these two are opposites. See, this is plus and this is minus. So you should be able to tell those two. One will be the mirror image through the y-axis, and then this one's also negative. So notice there's only one that's positive. Let's look at it. So is it possible to tell which one would be the -1? Get that one out of the way first. Which one looks like they're all on a straight line?
Well, no, those are negative that I'm looking at.
This one. See, perfect straight line. Negative slope.
Okay.
R
We're not looking at numbers there. We're looking
R is slope, B1, always at the same sign.
Okay.
That's how you know.
Okay.
So number 4 has a slope of -1. We'll get rid of that one. Now, which one is almost close to this, but it's not quite a straight line? Number 1. See it? If you drew a line through the middle of those, you have a couple that were just missing. So that one's going to be -0.996 for number 1. Now, of all the numbers in absolute value, 0.418 is the one that's closest to 0. So that's the one that's going to look like a cloud. Then the other two will be mirror images through the y-axis.
Okay, I see what we're doing.
So if you look at 3 and 5, they're mirror images.
Gotcha.
If you flip one through y-axis. So 2 is the negative. You can see that this would have a line like this.
Yeah.
So it'd be -0.418 for number 2. And then the one that's positive is 5. It has a positive slope. It's the mirror image of this one, which is a negative slope. And it's pretty tighter. See, these are both tighter grouped than this. This is more like a cloud. So 5 would be the positive 0.748 or 84, and 3 would be the negative. You agree?
Correct.
So what you want to do when you get these is get the ones that are obvious. These two are obvious. And then look for the ones that are paired, so that separates the third one that's remaining. So we did it right. Okay, this one, I got it written on the board, so you shouldn't miss this one. They'll ask you about this one. You should not miss this one. If we even do this. Yeah, we could do it. So 54 wild bears were anesthetized, and their weights and chest sizes were measured. Boy, it must have taken them weeks to do that. So there's the results. They got a really high correlation coefficient. It's positive. That means there's a positive correlation between the weights and the chest sizes. And these are your critical values because it's 54 for that number. So we're in the right tail. To be between those, we could be a pretty small R.
Yeah.
And you can see the p-value is 0. That means it's a significant correlation. And since R is positive, it's a positive correlation.
Okay.
Because R and the slope are the same sign. So for this one, you just write equals 0. And this is the alternative. This is the claim that there is a correlation, which means that rho is not equal to 0. Identify the correlation coefficient. Is it obvious? Which one is it?
Yeah.
No.
The correlation coefficient is 0.96522.
Just 3 decimals. And the critical values. So that's plus or minus 260. 6, 8.
And then do a positive and then a negative one.
Yeah, they put the plus and minus in place.
Yeah.
I forgot the decimal point, see that? Need a decimal point.
Oh, okay.
All right. Is there sufficient evidence to support the claim of a linear coefficient? So you see,
Yeah.
this is negative 0.286. This is positive 0.286, and we're way up here at 0.985.
965.
65. So we're in the right tail. Yes, there's a significant positive correlation. We're close to plus 1. 0.985 is close to plus 1. So it's statistically significant. And the reason for this is because the absolute value of the test statistic exceeds the critical value. So this exceeds 0.286, so we're in the right tail. That's the way they word it. They use absolute value.
So what if it switched it to a negative 965?
Then you say the absolute value is still exceeds.
Correct.
Either way.
Would it just be negative? Okay.
Well, if it was negative 0.965, the absolute value would still exceed the
Correct.
positive critical value.
Okay.
But you'd have to know that it's a negative and you're in the left.
Okay.
That's just the way they word it. So the test statistic is 0.965. Okay? So when measuring an anesthetized bear, is it easier to measure a chest size than weight? Yeah, it's easier to measure the chest size because you can take a picture. You could take isn't it easier to take a picture of a bear? And if he's sitting next to a tree or a rock and you know the size of the rock, you can estimate the bear's chest size. That way you don't have to get near the bear. You don't have to anesthetize it. You don't have to bring a.
Yeah, but it's asking when it's already and it's
Oh.
And it's
Okay, even if it's anesthetized, what's easier to do?
weight. You just throw the guy on the scale.
Yeah, but isn't it easier to just throw a tape around the chest?
Then you gotta lift up with an 800-pound bear.
You gotta lift it up either way.
Yeah, that's about the point.
See, it says yes, because it requires lifting the bear onto the scale. But anyway, I think it's A.
This is kind of like a unrelated question.
So it's A. Well, this is the idea. You don't want to go around anesthetizing and lifting bears. You do it. You do enough to update your data, but you can't do it all the time. And you want to know, so you take pictures and you know the size of rocks or trees next to the bear. You estimate based on the pictures the circumference or the bear's chest size, and then you can use the regression line to estimate their weight. You just need an estimate.
Okay.
And if
you know the chest size, you know it's weight.
Yeah, that way you don't have to have how many people you need to take the vehicles through the forest and do all this. You know, it's tough. It's a lot of work. That's why they do this. By the way, this is the correlation matrix. This is called a correlation matrix. See, paper is correlated with itself 100%, and glass is correlated with itself 100%. Now, the correlation between the two, no matter which one I call and which one I X and which one's called Y, the correlation between them is the same number. That's called the correlation matrix. Okay? Just so you might see one of those.
Can you do with as many correlations as possible, or is there always two?
No, there's multiple regression where you can have multiple. You can have the X's are called the predictor variables.
Okay.
And the Y's are what you're predicting. So you can have more than one predictor variable. Right now, we're only dealing with one predictor and one predictor.
Would that be like a 3D graph at that point?
Yeah, especially if you have multi-dimensions, you rely on the mathematics of it, because you can't picture it.
Correct.
When you have two predictors, you can, because then it becomes three-dimensional, and you can make a rendering of that that's fairly readable.
Okay.
But when you get to three predictors, then you need four dimensions, and we can't graph it. So you have to have a mental image of what it's doing.
Okay.
Okay? So we stick with the two dimensions because it's easier to understand. All right, so here's the deal. Let's see. This is the X and Y. They want us to find the scatter plot. So remember how we did this. We go to StatCrunch.
Correct.
So we got our X's and Y's. They label them as X and Y instead of variable 1 and variable 2. I go to stat, regression, simple linear, just like we did last Tuesday. I tell it X's are the X's and the Y's are the Y's. And then notice they don't have row here, and there's two of these. But see, slope is related to R, so this is row equals 0, row not equal to 0.
Okay.
That's my test. So we just leave it.
Okay.
That's all we need to do right now. So we hit compute, I hit this X, open it up, and then I go to a right arrow. So it's the parabola, upside down parabola, so it's D. Right?
Correct.
And then they're going to ask me for the linear correlation. So now I go back to the left arrow, and remember, they write capital R instead of lowercase r.
Yeah.
So it's 0.186. Or 816. I said that wrong, didn't I?
Yeah. I started looking around for 186.
Yeah, sorry about that.
Yeah,
That's my dyslexia. Okay, so using that, is there sufficient evidence to support the claim? So now what they're doing is they're asking us to find the CVRs. See, we're now at 0.816. We have to figure what these two are, and we based that on two things, N and alpha. And I gave you the handout. On your handout, you'll see this table A6. They give you two alphas, 5% and 1%, and then give you N. So we just have to find the N and what alpha they're asking us for. If they don't specify, we automatically use 0.05. So they gave us 0.05.
Okay.
See that? Alpha is what you call the statistical significance.
Okay.
How significant? In other words, that's what we're putting in the tail, essentially.
Okay. So then, yes, it is.
All right. So yeah. So there's two ways to do it. You can use the critical values. Now N is what? 2, 4, 6, 8, 10. There's 11 bears or whatever they are. So I find 11 plus or minus 0.602. And so the absolute value of this is greater than 0.602. And it's positive, so we're in the right tail. So once again, see, this is 0.602, and this is negative 0.602. And here's 0.816, we're in the right tail. The absolute value is greater than the critical value.
Okay.
So we know it's positive, so we're in the right tail. So there is sufficient evidence. But notice A says nonlinear. Be careful. This is nonlinear. It's linear. Because we're dealing with R. And then the last question is, identify the feature of the data that would be missed. Well, it was a parabola, so there is a pattern, but it's not straight line pattern. It's a distinct pattern, but it's not straight line. And we would have missed it if we hadn't looked at the scatter plot. But even in spite of that, it's still a significant linear correlation, and the reason for that is because the sample is not real. Smaller the sample, the harder it would be to do this.
So would that just be like pretty much the imperial for scatter plots.
I'm not sure which one.
Goes the,
No, this is a data plot. This is not quite like a scatter plot.
okay,
This is a little bit different. That's a good question. Scatter plots aren't data plots
okay,
because this is bivariate. That's the problem.
okay.
Data plots are just, all you have is x's and you have the frequency is the
Oh,
vertical.
is always,
Number frequency.
okay, gotcha.
These are just one data point. Each dot's a data point, but it has two values. It has an x value and a y value.
Okay,
So it's placed in the plane. It's called a scatter plot. It's not really, it's data, but it's for two-dimensional data.
okay.
Yeah, x's, when we measure x's and use that, what did you call it, the empirical plot, the normal
The
plot.
standard.
That's for single variate, univariate data, just x's,
Gotcha.
okay? Good question, though. That means you're on the ball
Trying.
there. I know. Okay. This one's kind of strange in a way.
Interesting.
And I normally don't do this, but I'm going to show you what's going on here.
That's interesting.
All right. So they want us to find, do the data appear to have a strong linear correlation? Well, if I put a line best fit, it's going to go right through the diagonal right there.
Yeah, with a very small, minimal.
But I don't know what the correlation coefficient is.
Okay, so you can't.
So I can't compare it to the critical values, you see. So I got to find the correlation coefficient. And they don't give me the raw data as a list. They give me the points. But they're easy enough to read.
Correct.
This one's 110. These are 81, 82, 83, 91, 92, 93, 10, 110, 10, 3, as far as order pairs. So what I do is I just go like this. Open StatCrunch. And I can type in my ordered pairs. So we said the first one was 110. So 110.
And then 81.
82. I'm just going to go in order like that. And then I'm going to do 91, 92, 93, 10-1.
It wouldn't matter how the data is inputted, correct?
As long as the pairs are matched.
Okay.
Doesn't matter the order. No, the order doesn't matter.
Okay.
As long as all the pairs are matched.
Okay.
All right, so now I just do stat, regression, simple linear. I tell it that the x's are in variable 1, the y's are in variable 2. So I don't care what they're called, as long as I just tell them the machine where to find the data.
Okay.
Everything else is the same. I just do it, and I make it a little bigger, just to show you that there's the diagonal line that I said it would be, and then the correlation coefficient is minus 9.06. So yeah, because if you look at for n equals 10, right? And do they give us alpha? See, they don't say alpha, so we'll just use 0.05. It's plus or minus 0.632. Well, minus 0.906, the absolute value is greater than 0.632, but it's negative, but it's strong, so I would say yes. Numerically, it's yes. Okay? Now they're going to say, what would the value of the correlation coefficient, what is the value? Okay, they're asking us, so we tell it, minus 0.906. Okay, we got it right. And then they're going to say, is there a linear correlation between x and y? Oh, now they're using alpha equals 0.01, so we have to use the right one for n equals 10. It's still plus or minus 0.765. We're still to the right or left of it, left of negative. All right, so it's still true, yes, because the correlation coefficient is in the critical region. It's in the left tail, which is the left critical region. Right? Correct. All right. Now they say what would happen if, what would the correlation be if we excluded the point that's up there?
Okay.
This
So
is,
you just
I
go
think
to
this is,
that and.
this is telling, so what we do is, options, edit. I'm sorry, no, that's not the one I want. What I wanna do is, I'll just close this. What I wanna do is just eliminate that, so I'll just delete, and then I'll do stat, regression, simple linear, and variable 1, variable 2, compute. You see the correlation coefficient 0. It dropped to 0. Because that's essentially, those are a cloud.
Yeah.
And if you think about it, the only line that best fit is the horizontal line.
So outliers really can.
Yeah, that outlier pulled that line of regression from a flat line to a line that made it look like it's heavily correlated. So you have to be careful. That's why a scatter plot will tell you a lot.
So is that used a lot to mislead?
Yeah, that's the way statistics can mislead you. Yeah.
Instead of dropping off, instead of just taking the group, the girl in that one outlier.
Yeah, you'd have to substantiate why you want to include that
For political consumption or for.
in your analysis. You'd have to have a good reason for including that. Yeah, because.
So they can't just throw in numbers when they want. They have to define why.
Well, yeah, that's the idea. To be above board. All right, so I usually don't show that example, but I thought it might be interesting.
Yeah, that one definitely was.
All right, so now we have internet users and award winners, and we may want to see if they're significant. 5%. Okay, so construct a scatter plot. So I close this. Now n is 6 here. See that? Small sample. Open the data in StatCrunch and do a stat, regression, simple linear. The X's are the internet users, the Y's are the award winners. Compute, open it up, and it's going to be, it looks like D. Yep. Now, I don't know if they're lazy or what, but if you notice, those are all the same pattern. They're just flipped.
All of them just
90 degrees or whatever, 90, 180.
Yeah. One positive, negative.
Anyway, the linear correlation coefficient for this is 0.783.
So no.
And it's probably not going to be significant.
It's not.
Because, well, we can use the p-value for that. I can tell you that. We see, so once again, you shouldn't miss these because it's always equals to 0, not equals to 0. It doesn't change. It never changes for any reason. 3 points. The test statistic is this number right here. See t-stat?
Okay.
For the slope. Remember, slope is related to R. The slope and R have the same sign. So there's your t-stat, 2.52 to 2 decimal places.
Okay.
2.52. We'll call it t-stat, t-statistic. And they want the p-value. The p-value is 0.066. 0.066.
Why are you only using slope value?
They give you the intercept, but it doesn't mean anything.
Okay, so that would
The slope is what's related to R.
Okay, gotcha.
Yeah. So the p-value you use the bottom one. And notice that the p-value is greater than what? 6.6% is greater than 5%. So the p-value is greater than the significance level.
Okay.
So there's not sufficient evidence.
Right.
We're not in the tail.
Right.
So there's not sufficient evidence. Remember, we're always trying to show that this is true. That's the claim.
Okay.
So the only way to do that is to reject the null.
So is that what you just did, rejecting null? Or
No, we didn't.
Null?
No.
Okay.
You see, if the P is low, then the null must go. Which means you cross that out and take this thing. But since the P is high, compared to what? Alpha. See,
right.
0.66 is high. So we're not going to we're not gonna negate the no, we're not gonna get rid of it. We don't say we support it, we just can't reject it.
Okay.
We never talk in positives about the no. We always talk in double negatives.
Okay.
We can't reject it. That's the way it is. That's
the part
the
that's
lingo.
running.
I know it drove me crazy for a long time. All right, so that's it. Now, just so we know, let's check critical values, because that's the old way to do it. Now, they don't give us the critical values here, but I gave them to you.
Yeah.
So
Yeah,
we look it up for n equals 6, alpha equals 0.05. What do you get?
You get below, or you get 9.950, which is, makes it within the code, or the correlation value.
No. N equals 6,
N equals 6.
alpha equals 0.05. 811. Now, is 783 absolute value greater than 811? No, it's less than. That means you're in the middle, you're between them. So that's why we wouldn't reject.
Okay.
So you can either use p-value or critical value.
Okay.
This is always going to be true for statistical testing. The old method is to use the critical value.
Why'd they change that? Because it was an extra step that wasn't necessary.
Because p-values give you an idea of how close you are to rejecting or not.
Okay. And then
You see, the
gives
points,
absolute value.
the 6.6, you can tell where it is compared to 5%.
Correct.
But the 811 and the 783 don't tell you much. You know they're pretty close, but it doesn't tell you,
How far away you are.
in percentage wise.
Okay.
So p-values give you percentages, which makes it a little more palatable to the modern sensibility, I guess. I don't know. But they did change it at some point.
I don't know, I like numbers. I
Well,
like exactness.
You just got to go with the flow. I mean, because it depends on whose paper you're reading. The other thing is trying to get you set for reading papers. You'll read papers about. You'll see p-value. You know what it means now.
Yeah.
You'll see test statistics and critical values. You know what those mean. Before we're done. All right. So here's another one. This is below overhead widths of seals measured from photographs.
Okay.
So you take, you're in a boat, you're measuring seals swimming, and you can't measure all the way around, but you can measure the width of the shoulders,
Right.
and that's going to give you a hint as to the weight.
Okay.
So because think about how problematic it is to capture a seal, bring it on board, measure it, weigh it.
You have to know.
I mean, you could do it for a few, but after a while, it's problematic.
Just to get your base values.
You can't just do it for all of them. You have to be judicious because you don't have a ton of money to spend on it. All right, so
you got PETA.
What?
I said not only that, but you got PETA for it. Doing that.
Probably. All right, so we're going to open the StatCrunch, and we're going to do a regression, simple linear. X's are the width, Y's are the weight. We compute, and the scatter plot is
The outlier at the bottom.
looks like D.
Correct.
Let's double check. The bottom one is like 7 and 130. This one is 7.
It would be at 100, 120, 140. Correct. Yeah, it's 7 and 100.
Oh, I'm sorry, 7 and 100.
Yeah.
110. It's D.
Yeah.
Because this one is 7 and it's 100 and a little higher.
Or about that.
Some whatever, but I would say D. That's the best one. Okay, we got it right. So we just had to check one point. We obviously eliminated these two.
Yeah.
It was a question of which one of those two. All right, linear correlation coefficient is 0.892.
And when it presents as a cloud, the line will be horizontal, correct?
Yeah, we'll get one of those before too long. So there's our correlation coefficient, and then they want to know what's the critical value. The critical values. So that here they gave us. Let's just get them off of here. Yeah. So we got n equals 6, alpha equals 0.01. So it's the right hand column.
0.917.
Plus or minus 0.917. Don't forget the plus or minus.
How did you type in that plus minus?
When you open up this It pops up down below.
Oh, okay.
There's a menu. Or you can write .917 comma minus .917.
so
You could, yeah, it doesn't, see, because they tell you put a comma, separate values. They'll also accept plus or minus. Because the absolute value of the linear, so because the absolute value of 8.92 is less than the absolute value, or the positive critical value, since 892 is less than 917, there is not sufficient evidence to support the claim. The claim being, we want to try to reject the null, but we can't. All right, so let's double check that. If you look at the p-value, the p-value is .017, which is greater than .01. Now, you say, well, why don't you use alpha as 5%? Well, whoever's running the study selects this ahead of time, because they don't want to make errors more than 1 out of 100.
Okay, so the .05 allows.
So .05, you only have 1 error out of 20.
Oh,
It's just,
so
it's more, this is more strict.
Okay.
It gives you a, you see, we're making that middle part much bigger, because
Right.
if you look at those, for .05, the critical values are always smaller.
Okay.
So that means you're shrinking your middle, making the tails a little bit bigger. You're willing to accept small, larger tails.
Okay.
All right?
Can you go less than the .01?
Typically, there's 3 popular alphas. 1%, 5%, 10%. That's a 99%, 95%.
That.
Although sometimes you'll see a 98, you'll see a 2% alpha.
Okay.
But alphas are set 1, 2, 5, and 10. That's the only ones I really ever seen.
Accepted testing parameters.
Right. Now, if you're doing medical stuff, it's always going to be 1%.
Correct. Okay.
But I don't see why they want it with seals, why they'd want to do that, unless the guy who's running the program says, no, this is what you said ahead of time. You can't change it. You can't get the p-value of .017 and go, well, I don't want 5%, I want 1%. No, after the fact, you can't change it.
Okay.
That's not kosher.
So that's
Yeah, you always set the alpha ahead of time.
No.
All right, so that's it for section 1. We're going to do section 2, which is talking about the regression line.
Okay.
Just the red line, which is the formula for it is always here. See, there it is. This is your intercept, V0, and this is your slope, V1. You see, slope's positive, R is positive. They're always the same sign.
Okay.
And then this is your Y, and this is your X.
Okay.
And technically, that's called Y hat.
Y hat?
Yeah, Y hat, because it's a predicted value. It's not a
Okay,
it's not a data value. And so you have your intercept, your slope, and then your X's are values that you just plug in. You say, okay, I'm going to predict for this X, what's your predicted Y? So this is pronounced Y hat.
Okay. Is it for that?
Yeah, and this is for the sample. For a population, it would be Y equals beta naught plus beta 1x. And you don't put a hat on this because it's a population. Right? At least I don't think you do. It'll come up. Let me see. I don't want to speak out of. It's coming up. We'll see in a minute. So let me close this. We're going to go to section 2, 10.2, regression. A couple of definitions to start, I think. Yeah, here it is. Here it is. They give us some values. So there's 2 numbers. So don't assume that this is B0. See, it says slope. So that's B1. That's B0. So you're going to put minus 369 in here and 125 in here. Well, you got to pick the correct one. And the only one that makes sense is A, because there is no such thing as X hat. And you have to have a Y hat. So the only one that fits the bill is A. So the minus 369 goes in for the intercept, the negative 369. And the slope, they say, is 125, so that's what modifies the coefficient for x. So that's your regression
So
equation.
you knew, it was y hat because it was, a sample, right?
Yeah,
Okay.
yeah.
I was seeing if that's how you determined if you were using the y hat or not.
Well, it says different hotels in a certain area are randomly selected. So as soon as I see randomly selected, it's a sample.
Okay. I was making sure that, that.
So what does the y symbol y hat represent? It's the predicted value of y, of the price. Okay? Number 2. Yeah, it is, I was right. You see, you don't put a y hat when it's for a population. So which one's which? The first one's for sample, the second one's for population. See, because theoretically, for a population, we have all the x's and y's. They're already grouped together as ordered pairs.
So you don't need.
We don't need a y hat because
Did you know?
it's already paired up with a specific x.
Okay.
That's the reasoning, I guess.
Makes sense.
I guess. What's the relationship between the linear correlation coefficient R and the slope B1 of the regression line? I've said it a couple times. They always have the same what?
Same sign.
Same sign. So A. Number 6. All right, suppose IQ scores were obtained for 20 randomly selected sets of twins. The 20 pairs of measurement yield an average X, an average Y, a correlation coefficient, a p-value, and a regression line. So we don't have the raw data. They just gave us the results of those 20 data points. So find the best predicted value for y hat given that the twin born second has an IQ of 101. Use alpha as 5%. Well, I can use the prediction line because the p-value is less than this, so the prediction line stands. There is a significant positive correlation because R is positive, so this is positive. So that is the regression line. So I can use that. So all I do is open up my calculator and I put in negative 13.16 plus 1.13 times the x value of 101. We want to predict.
I don't think they're looking at anything else.
Oh, sorry. Yeah, I see what you're saying. Thanks. So negative 13.16 plus 1.13 times the x value of 101. So this is the sets of twins. So the first, so x represents the
Okay,
set
so
of
you're
twins.
just filling the 101 into the already given equation.
Yeah, it says x represents the IQ of the second twin, and now you have a twin, you have an x value of 101. Could you predict the y value for the first twin, the IQ for the first twin?
Sure.
So we would predict 100.97, 2 decimal places. And then
Makes sense.
that's it. Yeah, that's an example of what we do. All right, so use the given data to find the regression equation. Okay, so now what I do is I open the data in StatCrunch. And now we're going to generate the equation like we did before. So I just do stat, regression, simple linear, compute. Oh, I forgot to select it. Sorry.
I kept doing that though.
X, Y, compute. All right, so the regression line, they say 2 decimal places. That means for both of them. So you see here, now they don't put Y hat. I gotta warn you, they don't write Y hat, but it is a Y hat. So it's 3.40, and X the coefficient, 1.1. If you want to put a 0, I guess we can, just 2 decimal places, doesn't matter. So create a scatter plot for the data. So it's the parabola, A. Identify the characteristic. So it's not a straight line pattern. So let me see something here. They didn't ask us, but can we use the regression line if we have to? And the answer is yes, because the p-value is 0, essentially.
Right.
So we can use the regression line. They didn't ask us that.
So why is that and then ignored that?
Which what?
The data that is ignored by the regression line. Why? How would that be ignored?
No, they said the characteristic of the scatter plot.
Oh, okay.
Because it has
Since
it has a significant pattern.
of curve.
It's not a straight line.
Okay.
See, if you get that outstanding correlation coefficient 0.912, and yet it's not a straight line. It's not really a straight line. But the data is close enough to a straight line that you can use for predictions. I know it doesn't. That's just the way it goes. Okay, that was 9. We'll keep going here. 10. Okay, this one's just X's and Y's again. So I'll close this and open up StatCrunch.
So I found you could just reopen StatCrunch on the next problem and it will close out the last step.
You can do that, yeah.
Okay.
I just make sure. Sometimes they back up and you got a bunch of them open. Sometimes I'll
try it.
So regression, simple linear, X, Y, Q. So the scatter plot is B. And what's the pattern here? Well, first of all, let's answer this question. So 2 decimal places, so it'll be 3.10 and 0.050. So that's the regression line. And what's the characteristic that you wouldn't notice if you didn't look at the regression? What's the characteristic? You have an outlier.
Correct.
So they call that, there's an influential point. They call it influential. So let's check a couple of things here. Right now, the correlation coefficient is 0.727. 2, 4, 6, 8, 10, 11. For n equals 11 at 5%, 602 would still be positively correlated, so it's okay. But it even be stronger. If I could eliminate that point, you could see that these data points would have a really strong straight line going right through them. It wouldn't be pulled up. See, you can see how it's pulled up away from them. See that? It's moving up.
Because especially with how
most if I got rid of that, it would go right through the middle of this.
Yeah.
Just be a stronger predictor. So the question is, when you're doing analysis for somebody, you go, now where did that data point come from? Do we trust it? Can we eliminate it? Is there a reason? Is there a rational reason we can substantiate just getting rid of it?
Do you have to, so in your sample size, when you get the outliers or the influential point, do you have to say, this is why I'm getting rid of it, or this is why I kept it?
Right. You'd have, yeah, because it's noticeable, so you'd have to make a statement about it. Okay. Typically, yeah.
So, like, say if you're doing a group of people, and that guy likes this stuff super spicy.
Whatever, yeah. Then you would, if it was detrimental to what everybody else was doing, you could substantiate getting rid of it. But if it was something that you just couldn't substantiate why you got rid of it, you'd have to include it and explain why.
Okay. Yeah. So you can't substantiate.
I'm just thinking about when I used to consult for people. You know, I used to consult with people. I helped like close to 10 people get their PhDs before I got mine because I was a statistical consultant for other students. They'd bring me all their stuff and I would go through analyzing their data, help them figure out what questions, how they could pose them, how they could answer them.
Oh, okay.
Yeah.
Because they're writing a paper.
They're writing a thesis, yeah,
Okay.
for their doctorate. Yeah, I did that. I used to. Yeah, it can be. It all depends on who's on their committee, giving them the directions that they want. Because some people narrow the context of what they can do. Like they'll say, this was even 20, 30 years ago, they'd say, no race,
Oh, okay.
no gender. You know, they don't want any, they don't want them making any statements about that. So, I mean, the data was there, but I couldn't do any testing. You know, like when you, like, well, like for a multiple regression, you couldn't include it as a predictor.
Why would you not though?
Because the word
I mean, I
came
guess
down.
you can't just
Like
find
I was working for boards of education. And this is what they
Well,
told me.
wouldn't you?
Well, I was working for other people. They would say, sorry, but we can't use that kind of computation.
But wouldn't that severely be a severe detriment to their own?
Yeah, but that's called politics. You can't, there's lines you can't tread across. They don't want it. Yeah.
But then you can't, so on a board of education, then you can't properly target the way to educate. You
Yeah.
can't adapt.
That's true.
So
It's political.
Because
Well, I know, but
they're sitting there wanting to help, their whole goal is to help, and then you get rid of the evidence that would help you, or the data
that might, yeah,
would
that
help.
might, yeah, I've seen that. It could be detrimental, yeah. That's how it goes.
And
That's how it goes. You know,
was
I
that
could,
angering? Was that angering? So you
it's just
told me-
disconcerting.
Okay.
It's petty.
Yeah.
But you know, sometimes people would come up with some stuff and they were severely handicapped, and like one gal had a statistical advisor because she was paying me on the side.
Okay.
She was in all things. She was in art history of all things. But this guy was telling her that she had to figure out how these subgroups were alike. And I said, yeah, but sometimes if you can substantiate that they're statistically different,
And that's how it would.
that could be something you could talk about, and
Correct.
it might be important. She ran it by him, and he stuttered and stammered. He said, "I'll get back to you." It took him like a few days or weeks to finally answer her. Yeah, that'll work, because he didn't know what the hell he was doing.
I was gonna say, because I would think that would be that if there's no first common way that they're connected, the only way that they're connected is that they're not connected.
Well, that's what I was trying to tell her. I said statistics. Numerically, this is how you can do it.
Yeah.
And I convinced her, and then she had to convince him.
I don't
But it
know.
gave her
You know,
something to focus on, because otherwise it was vacuous.
Yeah,
It was like, what are you going to talk about?
Yeah.
But yeah, I did one where there's this theory called field independence and versus field dependence. Field independence is learners who can take all the parts and put them together to make the whole.
Okay.
It's called additive and multiplicative.
Okay.
You can, if I give you all the parts, you can give me the whole. There's people that are subtractive. They don't see it. You have to tell them, okay, if this is the whole and this is the part, what's missing from the part to get to the whole? Because they got to be subtractive. It's called field dependence.
Okay.
They have a different mental structure. And I've met these kind of people.
Yeah.
They have a hard time learning math. And it turns out from the data studies that I studied, most of the people that are field dependent have lower IQs and they're criminally,
More like that.
they tend to be criminals. That's it. And you know what? That whole field was crushed. Because politicians didn't want to delve into that. Because if they could find a way to categorize criminals,
Yeah, that's a slippery slope.
yes, socially engineering them. It's like, and I thought, wow, I found something that was really important.
That is,
But I was told, no uncertain terms, don't go there because you can't put this on high school kids. Board of Education just came down heavy. Said, no way. I said, okay. I told the gal I was working with a doctor, PhD, and I was just a student.
would you be able to present, I guess, not opposing data, but something to go with it to show, hey, this is how you make them more, field independent?
Yeah,
Or is it?
for me, that's what I did, because when I met a person that was field dependent, I knew what to do.
Okay.
I knew you can't lay the lesson on them like everybody else. You have to pull them aside and say, okay, this is an alternative way to look at this.
So that.
And then they would appreciate that and they would help them.
Yeah.
Because I would tell them, you don't have to learn it the way everybody else does. You just have to learn it.
Yeah. Like, I don't know why they wouldn't just have separate classes defined by that.
Well,
one presented this way, one presented this way.
it's money. There's unions. There's all kind of bullshit. There's politicians, unions, money, funding. Believe me.
Make a continuous problem.
You have to constantly explain it, and after a while you just go, screw it.
Yeah.
I don't care. If you don't care, I don't care.
Yeah.
Anyway, I've been there, tried it. When people let me go on my own, I used to give them good results. Okay, here's the bears, chest size and weight. 6 bears. So find the regression equation. Okay, so
it's going to be 0.811.
You got it already. Cool, that's good. All right, so the chest size is the predictor, and the predicted is the weight, and the regression equation is negative 227.1 plus, I don't need a plus, my bad. 11.9. There's one decimal place. What's the best predicted weight for a bear of 50 inches? Now, remember, always check your p-value. If it's less than the alpha, here the alpha is 5%. So we're at 0.1%. So yeah, we're okay. We can use the regression equation. So it'll be negative 227.1 plus 11.9 times 50. 367.9. So the question then becomes, how close is it to the actual weight? Is it close enough? Now, once again, is it within 5%? So you take the difference.
367.
And you divide by the actual 397. So no, it's not close enough. It's 7.3% away.
Where did you pull 397 from?
That's the given.
Oh, okay. Okay.
That's the actual weight.
Okay.
This is 7.3% less than that. So if it was within 5%, then we would say, yeah, it's close, but it's not close.
Okay.
So the result's not very close. That's what they mean. Okay?
So would you
if they don't specify, you always use 5%.
Okay.
Now this alpha level is the significance level. The 5% here is just the 5% rule that we just commonly use when they ask us questions like this. You okay with that?
Yeah.
All right. That was 13. Let's do 17. Whistleblower systolic blood pressures for same woman, right arm and left arm. And we want to use the right arm to predict the left arm. Okay, so we open it in StatCrunch. See, these are small samples. That's one of the problems here, but that's how it goes. Regression, simple linear. Right arm is the predictor, left arm is the one that's being predicted. And R, let's see, y hat equals 61.9. And 1.1, one decimal place. Now, the regression equation is true, but guess what? The p-values.
Where'd you pull the 1.1?
Oh,
okay, it's point. Okay, 5. Gotcha.
So we're greater than 5%. We're at 7.9, well, 8%. So alpha, the p is not low.
Okay.
So we can't reject the null. That means we can't use the regression line. Okay. That means we have to find the y average. We can add them up and divide by 5, or just as a point of review, I can go to stat, summary stat columns and do left arm. That's because that's the y's. Okay. And the average is 155.8. You know, be careful, because if you forget, you're gonna use the equation, you're gonna get an answer that they're gonna say wrong. Don't freak out. Just go, oh, wait a minute. Did I check the p-value? Did I check to see if it's significant? Because, okay, here's the other thing. If you would have done it the other way, I closed that already. If we would have done it the other way, we would have seen that the R is 0.833, but what did you say the...
0.811.
I don't think so.
Or no, that was a different...
This is for n equals 5. It's 0.878. Plus or minus 0.878. And see, 0.833 is in the middle between them. So we can't reject the null. There is no correlation, which means you can't use the regression line. So either way, I like the p-value because it's always right there. If you open this up, it's always right there. It's the bottom one, the one that goes with slope.
Right.
And you just check and relate that to alpha.
Okay.
Okay, that was 17. Okay. This one kind of almost shows us a violation of the rule that we have, when we predict, we have to pick the x that's in the interval for the x's. In other words, I shouldn't go below 3.9 and I shouldn't go above 23.9 for my diameter.
Okay.
Because then I'm trying to regress outside my scope of my givens. But watch what happens here. You know the relationship between diameter and circumference? Do you remember?
R pi squared.
The circumference and diameter. Usually that's the radius in the circumference. Circumference equals 2 pi r.
2 pi. Okay.
And 2 pi is what? Or I'm sorry, 2r is what? D. So it's just pi d. That's the relationship. Okay. If you divide the circumference by the diameter, it's a constant ratio of pi. So look at the slope, 3.14. It's just about pi. See, that's everything's. Look at the r value.
That's what I was just like.
It's 1.
Yeah.
To 5, 6 decimal places, it's 1, which means it's a perfect fit. All right, so y equals, then what's 5 decimal places? 0.03012. And the other one, 5 decimal places, is 0.14049, right?
Okay.
All right. So the best predicted circumference for the diameter so we wouldn't expect on see 1.4 I'm sorry, 44.7, what am I thinking of, is way outside, it's way bigger than 23.9. We're way outside the range of our actual data. We don't expect it to be very good, but to one decimal place, it's spot on. See, they say the actual is 140.4. So even though 44.7 is beyond the scope of the sample diameters, the predicted value yields the actual circumference. And you know why that is? Because 44.7 times pi is 140.4 to one decimal.
And pi is a crazy number.
All right? So this is a case where they had some really good,
Factors.
well, some really good measurements.
Oh, okay.
Because it's not like, you know, the weight, the chest size and the weight of bears can vary. The same chest size could be different weight, and the same weight could be different chest size.
Yeah.
But the diameter is always going to give you the same circumference.
Absolutely.
It doesn't vary.
Yeah.
You know what I mean? So it's a different situation. Anyway, for what it's
I
worth.
like that one.
Okay, the next one is movies. So it's the budget versus the gross. How well does the budgeted amount predict the gross amount? 5%, and then we're going to have an X of 100 million, which is in our range. So let's go ahead and put the data in StatCrunch. And we'll do a stat, regression, simple linear. Budget is predictor, gross is predicted. And just, I'm going to look at the scatter plot. Not too bad.
No.
And the R value is 0.83840. That's not too bad, especially because it's a large sample. Well, let's see. Regression lines to one decimal place is 18.4 plus 1.3. Okay. All right. Now, can we use? Yes, because the p-value is low. It's 0 essentially, which means it's a significant correlation. It's positive because R is positive. And the best predicted, so I will take 18.4 plus 1.3 times 100. It's millions. So 148.4. So now they're not going to ask us to compare it. Let's check the critical values. Let's see, what's N? 2, 4, 6, 8, 10, 12, 14, 15. According to this, N, 15 and alpha, plus or minus 0.514. So there's a lot of leeway there. And we're at 0.840, so that's why it's significant. That's why the p-value is so small. It's a good predictor, apparently. Okay? And I think the last one here is earthquakes. 50 matched pairs of magnitude and depth measurements randomly selected from 10,594 earthquakes recorded in 1 year. So it's a random sample. Find the best predicted depth of an earthquake with magnitude 0.9. Okay, so first of all, we have to see if it's a significant correlation. So here's the measurements. This time I have a double opening here. So I don't need this anymore. Close that. And then stat, regression, simple linear. The magnitude is predictor. Depth is the predicted. And 1 decimal place, 10.7 plus 0.5. Careful. I don't like using 1 decimal place, but that's,
Yeah.
Now, are we going to be able to use the equation? Look at the correlation coefficient, 0.085, and look at the p-value. It's much larger than, that's 56%, much larger than 55%, or 5%. So we can't use it, so we have to use the average for y. So rather than try to add those all up, I'm just going to go ahead and do the stat, summary stat columns, and we want the depth column, the y column. And I hit compute, and the average is 11.4. That's the best we can say. We can just use the average value.
Yeah.
Let's look at the scatter plot, which I erased, but I'll go back to it. You'll see the scatter plot looks like a cloud. See that?
Yeah.
And see, the line of best fit is essentially a horizontal line, which means y equals. That's what a horizontal line's, remember, from algebra? Y equals. So we just go through the middle value was 11.4. There it is. Y equals 11.4.
That's why I was noticed as soon as you put that up there. I'm like, damn, that is awfully familiar looking.
Yep. And then we'll just have a couple of review questions here, and we're done. See number 2. Given a collection of paired data, sample data, what do we call that? What do we call that equation? Regression equation. Algebraically describes the relationship. That's the red line. That's the regression equation. And then number 3, which of the following is not equivalent to the other 3? X is the predictor.
Explanatory value.
Independent is the X. Explanatory is the X. So dependent is the Y. See, predictor, explanatory, independent all mean the same thing. Those are the X. That's a name for X. Remember, X is independent, Y is dependent.
Okay.
And X is the predictor or the explanatory. It explains what's going on with the Y. So dependent is the one that's not like the other 3. And then number 6.
X is what?
X is the explanatory or predictor. In a scatter plot, what is a point lying far away from the other data points? Now they gave us two
Influential point.
They gave us 2 choices here. It's either outlier or influential point.
Influential point.
You say influential, I'm going to say outlier.
How are they going to use 2 different definitions?
I know, I'm sorry about that.
Because point lying far away.
So I would just say this. You could say that an outlier is an influential point, but an influential point is not necessarily an outlier.
Okay.
They're not 1-to-1.
Yeah. They're trying to get the wrong answers. That's what they want.
All right, so that's it for homework number 4. Any questions?
No, that was it.
No?
That was actually pretty good. Well done.
I don't